This video covers electrostatics potential and energy in uniform electric fields. So up until now, we've talked about electric fields and forces. We said that electric fields go from positive charges to negative charges. So on the right, we have a picture of a positive plate and a negative plate. So our electric field will go from positive to negative. Now, here you have two charges placed in that electric field, and each of them experience a force. Now, because this is a positive charge, it experiences a force of attraction towards the negative side. And because this is a negative charge, it feels a force of attraction to the positive side. Now, the way you want to think about electric field is very similar to a gravitational field. Now, the sky is going to be considered positive and the ground will be considered negative. So if we place a mass in that gravitational field, it's going to be attracted to the ground. Okay? So we know that our gravitational field is 9.8 meters per second squared. That's our acceleration of our mass in that field. So then you can calculate the force of gravity acting on that mass by doing mass times gravity. But the very similar way, you can solve for the electric force acting on a point charge by multiplying its charge by the electric field. Now, we also know that we've seen in mechanics that if you put a mass at a certain height above the ground, it has potential energy associated with its position. Same thing for charges. If you put a charge in an electric field, it will have electric potential energy because the position away from a charge, in this case, are plates. Again, in mechanics, we calculated that potential energy by doing mass times gravity times height, as we see here. For electrostatics, we're going to calculate the electric potential energy as our charge times the electric field times distance. Again, you can see the similarities in between these two equations. Q is going to take the place of M, E will take the place of G, and D will take the place of H. In this case, we're going to see an example later where that's slightly not true, but we'll apply that for now. Now, this is electric potential. It's very important that we acknowledge a difference between what we just talked about, which is electric potential energy, and now we're referring to electric potential. Now, electric potential does not have an equivalent in mechanics. So everything up until now, we've been referring back to potential energy or mass. Here, electric potential does not have a mechanics equivalent. But we do know that the electric fields are incredibly strong, and even very small changes in distance can have huge changes into the field strength. So therefore, grouping E and distance D into one variable is very useful in electricity. So we're going to refer to this new variable as electric potential, and we're going to give it a variable V. Its units will have units of volts. The minus sign in this equation in the formula is often ignored. It's just to tell us the direction of the electric field, which in this case we already know. Now, we can substitute V into our potential energy equation and get a new equation for potential energy, which are down here at the bottom. So changes in electric potential cause changes in electric potential energy, just as changes in height cause changes in gravitational potential energy. Therefore, potential is visualized similarly to height and gravity. The potential difference between plates is measured in a manner similar to height. So again, a very useful equation would be to solve for the potential difference. This potential difference is a change in potential, and again, potential is just V. So while energy does not require a charge to move, a potential difference does. And again, you can start seeing the similarities here, that if we have a change in potential, then we have a change in potential energy. And remember that our delta is always final minus initial. So just like we saw in mechanics, if energy is changing, work is being done. It was a huge concept in energy. So work kinetic energy theorem that we used before states that work is a change in kinetic energy. Again, this is the net work done. In order for kinetic energy to increase, to have a positive change in kinetic, meaning our final is greater than our initial, we have to have a decrease in potential energy. Again, all of this is just stuff we've seen before. But now, because the same principle can be applied to electricity or electrostatics, then we can replace our change in potential energy with our other equation, Q times delta V. Here. Now, since we're applying energy equations, we can also apply the conservation of energy formulas. Now, since we don't have friction or other non-conservative forces, we don't have to worry about losing energy at any point or losing it to the environment. So here, all our energy at the beginning will be the same as all our energy at the end. Again, usually we start off with just one type of energy, which is our Q delta V, and we're going to have a final velocity at some point. Usually it's asking for the velocity right before we hit one of the plates. So at that point, we no longer have any potential. And so all you're solving for is your speed at those points. But we'll see examples of that in a bit. And again, to relate that to what we did in mechanics, if we had an object held at a certain height, here, then we can use, and it was at rest to begin with, and we let it go, then it was going to have some final velocity down here at the bottom. And we can use our conservation of energy equation to solve for that. Again, here you're just seeing a summary of all of the equations. I know it's a lot, but try to remember what they relate to back to mechanics. Again, the only one that doesn't have a mechanics counterpart would be electric potential, not electric potential energy. Again, this is probably the most important thing, that U is our electric potential energy and V is just potential. That has nothing to do with the charge placed in that potential. Okay? Our potential energy means that we actually have to put a charge at that point before it can have potential energy. In this situation, we're looking at two different plates, one positive, one negative. We know that the electric field line is going to go from the positive plate to the negative plate, as these green lines show. Now, what we are looking at here are drawing equipotential lines. Now, equipotential lines means lines of equal potential. Now, the object that is the most positive is considered to be at high potential, and the object that is most negative is considered to be low potential. So here you have these values labeled. 0 volts is when we have zero potential at the bottom, and 6 volts is when we have a high potential up on top. So the potential difference between these two plates is 6 volts. Now, just like masses that go from a high height to a low height when let go, positive charges are going to move from high potential to low potential. Negative charges, however, are going to move in the opposite direction, from low potential to high potential. Now, you want to think about potential as electrical pressure, like water pressure. You know that water pressure from the water company moves water to your home. Electrical pressure from a power company is going to move electricity to your home. Now, the term high voltage means that there is a high potential, okay, a very high likelihood that the electricity will move from a high potential to a low potential. The potential by itself cannot harm you. It is a measure of the pressure on the charges and the likelihood that charges will move from an object labeled high voltage to you, low voltage. It pretty much means, don't get close to me. I have the ability to send lightning bolts at any object with less potential than me. Now, the size of the lightning bolt, which is where we're going to look at next, has to do with the current or flow of charge, and this determines whether injury or death occurs. Now, like we said, V, or volt, or potential, is going to be equal to our electric field times the distance, or height in our case. Now again, this does not have any mechanics counterpart like charge did in mechanics. Again, potential is V measured in volts. So if we have a potential of 2 volts, it is written as V is equal to 2V. This will also be called electrostatic potential, electric potential, or just plain potential. So anytime it's asking for any of these three things, you're just referring to V. Now, there's a huge difference between the potential difference and just potential. Remember that potential difference is that delta V. In this example, you have two charge plates that generate a 20 Newton Coulomb electric field, and these are separated by 15 centimeters, and you're asked to determine the speed of the electron passing or exiting the plates. Now, what this means is that one of the plates, the positive plates on the right-hand side, has a hole in it, but it's still enough electric field so that it attracts it through this hole. So to start off, we can use our potential energy equation. So at one point, because my electric charge is at the negative plate, and we said that negative charges are moving from low potential to high potential, then that means we have entirely potential energy at the beginning, and at the end we'll have entirely kinetic energy. So for electricity, our potential energy is QV. 1/2 mv squared is still our kinetic. But now remember that our V, or voltage, or potential, is just ED. Here, what we're trying to do is solve for V. We know that it is an electron, so we have Q. We know the magnitude of the electric field. We know the distance that these plates are separated by. You know that your mass of an electron, you can pull that information from your constant sheet. What you're trying to do is solve for V. So that means QED times 2 divided by M, and then all of that square rooted is equal to V. So then you can plug in your numbers. You have the square root of 2. The charge of one electron is 1.6 times 10 to the negative. We have, I'm just going to write it, times 10 to the negative 19. You have electric field, which is 20 Newton coulombs, so it's fine like that. The distance is 15 centimeters, that's 0.15 meters. And then the mass of an electron is it is 9.16 times 10 to the negative 19. I'm sorry, 31. Jeez. And be sure to put all that into the calculator to get a value of 1.06 times 10 to the 6th meters per second. Now, if we saw this exact same example with a proton instead, we would have to look at a positive plate. So a proton would move from high potential, which is by the positive plate, and move toward a lower potential, which would be at the negative plate. But the process would be exactly the same, except you would need to use the mass of a proton and the charge of a proton, which is the same as the charge of an electron. So in the last example, we saw an object like a proton or an electron accelerate through a potential difference. Now, there are many ways to convey this well-known acceleration. If the problem says electron or proton accelerated through a potential difference, what it's referring to is the picture that we just saw. This is also if it refers to an electron or a proton beam, or any diagram showing a charge moving along a field line between two charged plates. And we'll see a lot of examples in just a second. All of these are examples of an acceleration through a potential difference. Now, you don't have to write all of these equations down or all of these examples down. I just want to show you a few that you might see. Now, on the far upper left here, this is the one that we just saw, where an electron is located at the lowest potential, and again, an electron moves from low potential to high potential. Here, you have a battery, so we saw this symbol of a battery before. This battery charge attached to two sides. Now, because of the battery, one side is going to have one charge, and the other side will have another charge, and usually a problem will ask you to determine what's the charge on each of these plates. Again, here, very similar to our plates example at the beginning, you have a negative side and a positive side. Again, this charge is going to accelerate through them. This bottom one down here is very similar to this one up here, although it doesn't have a boxed off area saying that these are plates. Because you do have charges on both sides, it's still going to accelerate from one side to the other. Now, for all of these, the good thing about it is that you're going to still be applying this energy equation, that our potential energy at one point will be equal to all of kinetic energy at the other. Now we've seen this symbol before. We're going to see it again in circuits. This represents a battery. On the longer side of the battery, this is going to be a positive side. On the lower side, on the shorter side of the battery, this will be a negative. So this is positive, this is negative. That means if this charge is accelerating from left to right, it must be an electron. That's the only way it would naturally move from a low potential to a high potential. Same thing here at the bottom. This side must be negative, and this charge must also be negative in order for it to accelerate to the other side. Same thing here. It must be a negative electron. So all of these examples are showing the exact same situation. So that's why batteries have potential. Now this last example has several steps. It says a charged particle accelerates through a potential difference of 40 volts in a set of vertical plates. It enters a set of horizontal plates that are 10 centimeters long with a 20 Newton per Coulomb electric field. You're asked to first determine the sign on all the plates. Determine if the accelerating particle is an electron or a proton and draw its path. Now, we said previously that this battery shows that the side on the right is positive and the side on the left is negative. That means this plate is positive and this side is negative. That means if it's accelerating from low potential to high potential, this will also be a negative charge. So it's going to accelerate through there and have a certain speed as it comes out. Now, over here on the right-hand side, you have electric field lines that go from top to bottom. That means that the top must be positive and the bottom must be negative. Now, if we have an electron that goes in here, right, it's going to follow a straight path until it enters that electric field. Once it enters that electric field, it's going to be attracted to the positive side. Again, always moves from low potential to high potential. So it's going to take a path that looks like this. Again, for these kinds of problems, you're going to want to think of projectiles. Now, this part asks us to determine the electric field direction between the left set of plates. So our electric field, again, goes from high to low, or positive to negative. So our electric field is actually going like this. Now we're asked to determine the speed of the charge exiting the hole in the first set of plates. This is identical to the first problem or first example we did in this section. So, if we want to determine the speed, then we can use our potential energy equation. That says Q times V, which is Q times ED, is equal to 1/2 mv squared. Again, our charge is an electron. Our electric field is given, and the distance between, actually it's very important, this electric field is here. This distance is 10 centimeters or 0.1 meters. Now, we don't know the electric field and the distance between these two plates, but we do know the electric potential. So we're going to use that information instead. And we're asked to solve for the speed v. So that means 2 times q times v over m square rooted gives you lowercase v. So I'm going to start adding some little flair to my velocity so that you can tell the difference between volts or potential and velocity. So again, after you put in all your numbers, you should get a velocity of 3.75 times 10 to the 6th meters per second. Now part D asks you to determine the vertical deflection in the second set of plates. What that means is it's asking you to solve for delta y. Now you really want to think of a charge going into a field vertically. So it's shooting off like this, right? It's moving through here. When it enters the field, then it follows this path. This is very similar to a horizontal projectile, and it's exactly the way that you're going to be treating it. This is just an upside down horizontal projectile. So before you can solve for the delta y, it's helpful to know the acceleration that it's going to experience when it enters these plates. Now, the acceleration comes from F equals ma. But what F are we talking about? In this case, we're talking about our electric force, which is Q times E. Now, my E is my electric field. My Q is the charge placed in this electric field, which is an electron. So, to solve for A, we divide by M. So once you put in all of your values, you should get an acceleration of 3.51 times 10 to the 12 meters per second squared. Again, now that you know the acceleration, you can solve for delta y by finding one other piece of information. Now, we know that it's going to enter this field on one side, and it's going to continue to fall until it either reaches the end or it leaves the field that it's traveling in, meaning that it comes out on this end. So we know that the horizontal distance it will travel is the length of one plate. So we can actually use that information to help us find time, which is going to be another piece of information that's going to help us find delta y. So again, the goal for this is we're trying to use one of our kinematic equations, namely delta y is equal to v naught y t plus 1/2 a t squared. Again, to solve for delta y, we know our initial velocity in the y direction is 0 because we only have a velocity in the x direction here. So what we can do is solve for time. Now, we know that our velocity in the x direction is constant for projectiles, and that velocity is equal to distance over time. So, t is equal to x over vx. Now, vx is a velocity that we had as we left the first set of plates. So again, our distance is 10 centimeters long, so that's 0.10 meters, divided by our velocity as we left the first set of plates, which was 3.75 times 10 to the 6th power. This gives us 2.67 times 10 to the negative 8 power, and this is our time. Again, we're going to use this information as our time here, use our acceleration from the previous problem here, and then use all of that together to solve for our delta y, which comes out to be 0.0012 meters. Again, this number makes sense because that's about 12 millimeters, and these plates are only 10 centimeters long. So we shouldn't have had a very long time in order to fall.